Okay, I'm handing over the stage to them.
Sure,
Thanks, guys.
Hello, guys. Good morning and welcome to KCD Kochi. I am Ashik JM. I lead the internal cloud platform team at Cloudera. I'll be doing a presentation on HCI, our KubeVirt journey, along with Sibiraj IL. He's a staff engineer in my team.
Hello, everyone.
So before we start, let me quickly check who all know about, who have heard about Cloudera, or who all know what we do and things like that. Can we have a show of hands on who already know what is Cloudera, or you're familiar with what we do and stuff? Okay, I don't see much, but yeah, let me then start by introducing. We are the creators of big data ecosystem powered with open source software. So Cloudera Data Platform, CDP, we are an open data lakehouse product which enables organizations to do data analytics on any kind of data anywhere, like be it a private or public cloud. So shipping an open data lakehouse product can be very challenging. So our CDP is based on over 30 plus open source projects, and we support a lot of Linux operating systems also. So our support matrix is very broad. Moreover, we also integrate with multiple databases, security products, and also physical appliances. And we have dozens of releases per year, including the major, minor, and odd fixes, and etc. So as a result, what happens is we have thousands and hundreds of tests that we run around across thousands of clusters per release to certify quality. And how do we meet this demand, right? We have a container cloud, internal container cloud, and Apache RM. Apache Yarn is the resource manager and scheduler in that cloud, along with the Docker container, Docker running as a container runtime. We provide VM-like containers, which are ephemeral in nature, to the teams for their product testing and development. We call it VM-like containers because these are containers, but we give them a dedicated IP address, host name, and a stable name resolution. This is kind of a requirement for our product to be tested and stuff. And this cloud has been adopted by most of the products across Cloudera. We have been running this for last 6+ years. Let's look at some numbers for reference. We have around 700 bare metals, which give us approximately 220 TB and 27,000 cores. And in terms of scale, on any given day, you will find around 8,000 plus containers as part of 2,000 plus clusters with an overall memory usage of 80%. And during peak release times, or when multiple releases collide, we kind of have around 95 to 97% of overall memory usage. So let's look at a few of the gaps that we have in this container cloud. As I said, this has been set up more than 6 to 7 years back. So first foremost is the VM use cases. So we can all agree that we live in a container era, right? Everything has moved mostly to containers. But then again, the relevance of VMs have not died completely. So they are still relevant for few of the use cases. We still see one or the other use cases in between where they need VMs isolation in terms of non-namespace kernel parameters, or a network and things like that. So those use cases were on the rise, and although we were able to work around these use cases in our current container cloud, those were getting operationally heavy. Recently, we had one FIPS enabled and all those, and then users, some of the customers needed OEL, UEK, and things like that. So this was one gap that we were, that's on the rise for us, and persistent volumes. So stateful applications always had issues with this. When a node, when with the 700 bare metals, you will definitely have one or the other, reasons for churn, and the stateful applications do get impacted when the state of the containers is ephemeral. And the ephemeral nature also caused issues for us during host maintenance. We didn't have, we had to wait for the users to drain their workloads from a node in case we have to do some upgrades, or take it out for any kind of hardware maintenance and things like that. So even a Docker upgrade on these 700 nodes would take us months. Apache Yarn by design actually installs a Apache application manager along with each of the cluster that we deploy. Although it takes only a few GBs, at our scale, when it is deployed for every other cluster, it kind of comes around to, in order of TBs. And most of our control plane components are also EOL. And this is where we started our, we started chasing some solution around this, and we started, and we were, we had this thing in mind that we didn't want multiple environments where, one where the containers run and, the other one where, users can go for the VMs. It is both, operationally tedious and also tedious for the users. So we always were this one sure that we needed something which supports hyperconvergence, multiple form factors, and that is where Kubernetes comes into picture for us. So Kubernetes did show promise. It it had very good resource management capabilities, and it is scalable, highly available, and both form factors. Right? Once KubeVirt came in, you had support for both containers and VMs. Okay, it had support for persistent storage, loads and loads of plugins and controllers to choose from, and an ever-growing community and support. So this all did work in this one, but it did come with challenges, and these challenges were mostly because of our unique requirements that we have for our product, right? So first thing was we wanted a stable IP address with external connectivity for both the pods and VMs that we deploy. Second thing is, because we are giving an IP address with external connectivity, we also had to give them a stable name resolution. So KubeVirt by default suggests or recommends Kube secondary DNS, but then those only handle VM DNS names. So another thing with KubeVirt was the use of data volumes. So by default, KubeVirt used data volumes to import the VM images when we created images, and even with few MBs, it used to take a couple of minutes. And few of our pre-warmed STP images and all those are in terms of GBs. So that also was kind of a factor that was a challenge for us. And live migration support. KubeVirt by default did support the live migration eviction policy, but there was nothing in the documentation which would clearly point you out how to make it with a zero downtime. We always saw a small blip when we were live migrating the VMs. And multi-tenancy, this was also a deal breaker for us. Apache Yarn gave us very complex hierarchical resource quota management capabilities, and we wanted something that would do the same for us in Kubernetes also. So here is where our journey gets exciting. We kind of now will walk you through how we solved all these challenges with the Kubernetes and KubeVirt. And all the innovations and stuff like that is what we are going to talk next. So I'll start with the high-level architecture of our current cloud. What you see here is a Kubernetes cluster, RK2 based. It's the components on the screen are the default ones that you see, K8s control plane and worker nodes and stuff like that. The first thing that we did is to replace the default scheduler with Apache YuniKorn. So Apache YuniKorn is a very powerful K8s compatible scheduler, which gives us very good quota management abilities. Along with that, we installed KubeVirt. It's an operator which lets, which controls and which allows us to create VMs. So VMs are defined as CRDs in the Kubernetes clusters. Along with that, we also have our Cloudera Infra control plane. It has 4 components within itself. One is a provisioning API. This is the endpoint for users, which does all the distribution and stuff. There is a quota manager, which actually allows us to define quota, hierarchical quota, and it works along with YuniKorn to enforce those quotas. We have DNS manager, which will manage DNS for both pods and VMs, and will add A records against the secondary routable IP address that we add to these VMs and pods. The workflow management, we use Stackstorm. It helps us with the event management and workflow management in the cluster. So now let's double click on each of the components and also the other challenges that we discussed in the previous slide. I'll briefly give you this one about how we solved the DNS problem that we had. So our requirement was to have a stable name resolution for pods and VMs, and one of the main challenges, right? So what are the challenges? So when you install Kubernetes or KubeVirt and all those things, you get core DNS along with that, and it only monitors the pods in the cluster, and it doesn't have. It only considers the network, which is the IP address on the default pod network, and the DNS names are also not user friendly that we can give out to users. And KubeVirt recommends kube secondary DNS. The vanilla kube secondary DNS also has few drawbacks. One is that it only looks at VMs and doesn't look for pods, and there is no PTR record as of now. It's in progress, and the DNS names were not again user friendly. So how did we work around this, right? So we did go with the kube secondary itself. But okay, so before I explain how we what additional things we did here, I'll give a quick overview of what kube secondary DNS does. And so you see a VMI controller, so that keeps watching the VM instances. As and when there is a creation or deletion, it talks to zone manager and updates the zone files accordingly if it is an add or a delete request, and then core DNS reloads each time there is a zone file change. What we did was we forked the kube secondary DNS and we added a pod controller along to it. So now what happens? These two controllers keep an eye on, watch the events for VMI and pod creations and deletions, and update the zone files accordingly with both A records. Along with this, we also added reverse DNS support, and also we simplified the A record and made it more user friendly. And this is how we solved the DNS architecture. We'll give you a gist of this also in our demo that we have at the end. Now I'll hand over the session to Sibi, who will give you details about the other components that we have in the architecture, and also a few of the other challenges that we faced. And also we'll have a demo at the end of the session. Thank you, guys.
For demo, the Wi-Fi is connected. Yeah, Marriott is okay. Hello everyone. Let's briefly look at the network architecture. Our main requirement here is to bind a stable IP, and that becomes a deal breaker for us to get that IP assigned to the pods and VMs for the external connectivity. And the main challenge is there are two different CNI which we explored. That is the default CNI that comes with the default RKE to Kubernetes vanilla cluster, and that doesn't have the support for having the additional network interface. And additionally, we will not be able to attach the routable IP to that CNI. By default, Kubernetes comes with its own CNI, and that IP will be only be routable within that Kubernetes cluster. So something that can be reachable from the external to the cluster, that was the main requirement to disregard the default CNI. And then further we explore the multi-CNI, and that is the main CNI to configure the secondary interface on the pods and VM. And to have that multi-CNI, there is no standalone deployment. It can't be deployed as a standalone app. So it has to work with the conventional network CNI plugin, and there is no support also it has for pod networking, so it has only VM side. So we have to associate with this default CNI. And the IP address management side, because if the CNI is there, it has to be the responsible for assigning the IPs and pods. And by default, the multi-CNI handles the IP per host level. So that means each worker level only we can track that IP assignment for the pods and VMs. So in order to address that challenges, the solution we came up with is the multi-CNI that sits top of that network architecture, and it configures the bridge interface on the host network where the VM and pods attach to that CNI. And there is a enum state operator that takes care of configuring the bridge interface in all the nodes. There is a worker nodes in the cluster. And there is a whereabouts CNI that takes care of providing tracking the IP address for the VMs and pods. So this is the overall flow of the pods and VMs network architecture. So here is the network interface description. On the right hand side, you can see that it's kind of manifest to create this multi network interface. So by default, it includes all these characteristics of the network. That includes the bridge interface, that is the interface name where the pods and VMs are attached in the host. And then there is a whereabouts CNI plugin type. So that is the one takes care of providing the unique IP in the dynamic way for the pods and VMs, and it provides that IP from this range which we define in that manifest. And in the VM case, we need to define the network interface in the manifest, and that name should match with this network attachment definition manifest name. And for pod case, this particular network attachment definition name has to be associated as the annotation in the pod manifest. So let's move on. So provisioning time. So speeding up the provisioning time is the deal breaker, and by default, when you have a Kubernetes-based KubeVirt cluster, it comes with the data volume, persistent volume type. So it provides two different way of configuring the data volume. The one is the ad hoc based data volume, and then second thing is the pre-allocated data volume. The challenge with the ad hoc based data volume is for each of the volume creation for the VM, it has to fetch the data from the external source and creates that persistent volume in the cluster. Whereas in the pre-allocated data volume, we have to create that the data volume for each VM in advance. So that means there are chances to lose some storage space in the cluster. So overall, when we use this data volume based persistent storage for the VMs, and it prevents the VM to start until this data volume prepares that VM image into that persistent volume. So that is the main problem we experience with the data volume. So the solution we ended up with is the backing image support provided by the Longhorn storage system. And this supports the QCOW to like a KVM image and as well the ISO image that will be mapped to the storage class. And we create the storage class for individual operating system. So in this slide, you are seeing the manifest of this CentOS 7 storage class. And each VM will request for the persistent volume through the storage class. And then that persistent volume will be created in the Longhorn and that attached to the VM. And overall, it just takes a few seconds to launch the VM by using this backing image support for provisioning time. So moving on next. So live migration is the key factor in any of the VM solution. And the same way in the KubeVirt also, we explored the possibility to have the live migration support, so that if the live migration is there, when and there is a problem to the VM, and for example, when node goes down, that time obviously the VM also will be lost, right? So to avoid those things, the live migration came into the rescue, so that the end user workload will not be impacted during this migration happens between the worker nodes. So to configure that, we have to enable the live migration eviction strategy in the VM manifest. Along with that, the persistent volume has to be set as the RWX mode, and so that the concurrently the volume can be accessed from multiple nodes when the migration happens. So in the future on this side, to improve that migration speed, so we are working on to provide that configuration in the dedicated network, so that the data segmentation copy can happen through that dedicated network channel, so that the migration effort can be seamlessly improved. So we will have the detailed demo in this about the live migration. So quota management. So we need the efficient quota management along with that the scheduling for the VMs and pods. So for this we came up with that Cloudera's own CDP control plane manager that comes with the quota manager along with that Apache YuniKorn. So the quota manager takes care of providing the hierarchical based resource quota, and it works with the Apache YuniKorn, so that the scheduler which has the capability to define the quota enforcement and preemption and the advanced scheduling and then the access control is and many more. And this Quota manager and YuniKorn works together in the same Kubernetes cluster to define the quota hierarchical based for the VM workloads. So let's look at the demo. Yeah, in this demo we are deploying the pods and VM. First we are deploying the pod, and along with the pod there is a persistent volume claim that is attached to that pod, and pod also created. Now we are deploying the VM. Along with that VM there is a persistent volume. So let's look at the pod status, and right now it's in the creation state. Let's wait for that pod to come up. Yeah, it took around 18 seconds to come up that pod. And let us check the VM status. And it took just 17 seconds, imagine, to get the IP and all the setup for the VM to launch in the Kubernetes cluster. So let's explore the IP address assigned to the pod and VM. So this will get the external IP attached to the pod, and let's next check the VM external IP attached to that VM. Yeah, this is the VM IP spec. This includes all the external IP configured in that VM. So let's look at the DNS entry. This is where the DNS solution is powered by the Kube secondary DNS, and here is the format. And this is the VM host name, FQDN name, and the first name portion denotes the VM name, and the second name, it's in this case a default, it's a namespace name. It's all tracked under the single namespace, and then the VM or pod, either of the type. And then the yprod ext site as a subdomain, and this is where we mentioned earlier the Kube secondary DNS comes with the default support for VM, and we forked that and added the pod support to have the external connectivity attached to the VM and pod, so that any of the pod and VM can be accessible from the outside of that Kubernetes cluster. So let's look at the live migration. So here there are two VMs, demo VM and demo 2 VM. First let's trigger the migration for this demo VM, and that is running currently on the host 14 worker node. And let's monitor the migration status. So if you use this command, it will tell you what is being tracked in the backend. So right now the migration is running. Once that is done, it will move to the succeed state. So let's now list out the VM and check where that VM is right now. It's running on. So see, in the host 14, it moved to host 17. So all happened within the 30 seconds of time to migrate entire VM along with that persistent volume. So let's log into that VM where that migration happened and check the uptime. Now you can see that the uptime is just 1 minute. So that means there is no downtime to that VM. It's all happened in the backend in seamless way. So inter VM connectivity. So we have two VM and one pod. Let's log into one VM. So VM also we can just access like SSH, how we access that AWS EC2 instance, right? The same way the KubeVirt VM also can be accessed by using that external host name. You just see that we are not exe into the pod way. This is the direct way. So we'll try to ping another VM. It's a demo 2 VM. Yeah, we can see the response. And let's ping the demo pod. So we should be able to get that response by that results to that external IP. And yeah, this is our Cloudera manager. This is a CDP Cloudera manager, and we deployed this Cloudera manager running on the KubeVirt based cluster, and this is a version. And these are all the hostess backed by this Cloudera manager. You can see the list of hostess here. These are all the KubeVirt VMs. So traditionally, Cloudera manager can only be able to run on the bare metal hostess or the AWS instance, but this is the first turn. We try to make that possible on the KubeVirt, so we succeeded by deploying all the VMs by addressing all the gaps. Yeah, so this is the overall dashboard. Demo is done. We would like to thank all of our key pillars. These are all the CNCF project to complete all these components together to achieve this KubeVirt based hyper-converged infrastructure. Yeah, thanks. Thank you. Yeah, thank you.
5 minutes is there.
5 minutes. Yes, yes.
We can have a very quick Q&A session if anybody has questions.
It is a nice presentation. You guys did cool things around KubeVirt. My question is, like, how will you provision an image? Like, how the provision process takes place? Or will we use the container registry itself? If we use container registry, how it will translate it to QCOW to image? And my second question is around security. So if we have SSH access to a pod, let's say to a VM, it allows for lateral movement across the pods and other VMs, right? So how we can prevent those things?
Right, got it. Yeah, we'll take the first question. So for VM image provisioning, so it has to be a QCOW image, any of the QCOW image available in the outside, or you can create that image as same as in the KVM hypervisor we used to create that, right?
Okay, if it is a quicker to image, so how will you import into keyboard?
Yes,
like,
that
it
is
a
where
container registry or?
Okay.
I think he's asking about. So basically, it will not be in a container registry.
So
You will have to have it in somewhere which can support VM images. Okay, because those will be different format, right? You cannot have the Docker Hub or Docker registry. So that's why you see a HTTP URL. So it supports different kind of imports. Okay, the backing image data source parameters, right? So and also it supports all kind of VM images. So basically those will be all VM images, not the container images. Yeah. And I think lateral movement, right? So that again still is a small concern because you'll have a single network within the this one. But the secondary network that we give in the CNI, right? That is where we can control if you want silos within the pods.
Also, can we have some sort of security group or firewall inside a VM so that we can at
Definitely,
least,
yes.
get a
So
small
it will be like a totally isolated VM where you can have, it will just behave like any other VM solution. So it will have its own what is that? If you install IP tables, you can isolate it from the environment and everything. But again, here is where you give in the whereabouts is where you give the range, and that is the range that gets assigned to each of the VMs and pods. Here you can segregate, if you need multiple networks within that is what you meant, right? You want one group of VMs not to talk to this one. Yeah. Thank you. You want to add something, sir?
No, that's fine. Thank you.
Any other questions? Okay.
Okay. Thank you, guys.
Thank you very much.
Thanks for it.
Thanks, guys. Give them a round of applause, please. Yeah.